what happens to a charged particle in an electric field? All of you know this is a very simple question. When a charged particle is kept in an electric field, what happens to it? So, see, if this is an electric field. In an electric field, if you're keeping a charged particle, from the definition of electric field itself, you know that it's a space around a charge where electric forces experience. So, clearly, in an electric field, if you're keeping a charge, it will experience a force. All of us are familiar with that. So here I'm going to consider, see, you can see the board. In this region, let us assume there is an electric field. Okay, and let us take its intensity as E. So the intensity of electric field in this region is E. Okay, so in this electric field, I'm going to place a charge particle. Look at this. At this point, it's a point in an electric field. Please note that its intensity is E. In this electric field, I'm going to place a charge. The charge magnitude is Q. So, situation is very clear. There is a charge particle Q. It is kept in an electric field of intensity E. So, all of us know that this particle will be experiencing a force, right? What is the formula for that force? Hope all of you remember it. The force F is equal to charge times electric field. Intensity, because intensity of electric field is the force experienced by a unit positive charge. It's a force experienced by a unit charge, 1 coulomb charge. So 1 coulomb charge is experiencing E force. So clearly 2 coulomb will be experiencing 2 times E, 3 coulomb will be experiencing 3E. Like that, Q coulomb, Q charge will be experiencing how much force? QE, right? So all of you know this formula, force F is equal to QE. Remember, force is a vector quantity. Okay, now we are going to understand what is happening, what is going to happen if a dipole is kept in a uniform electric field. Dipole, you know what is a dipole? Dipole is a pair of equal and opposite charges. So if there is plus 1 coulomb and minus 1 coulomb are separated by some distance, that arrangement is called a dipole. So in this diagram, you can see that there is only one charge. One charge is kept in an electric field. It is experiencing a force QE. In the same way, we are going to keep a dipole in an electric field. So we are going to understand what happens to a dipole in an electric field. Okay, so let us recall a dipole again. What is a dipole? It's a pair of equal and opposite charges kept at a small distance. Okay, so here I am going to show you a dipole. Look at this. This is one charge. If you are taking this charge as minus Q, to make it as a dipole, we need to bring another charge, but its magnitude should be plus Q. So look at this. Minus Q and plus Q. Separated by some distance, some small distance is called what? An electric dipole. So clearly this is an electric dipole. This arrangement is called an electric dipole, right? And you know that normally the length of the dipole, the distance between the two charges is represented by 2L or 2A. Okay, then the strength of a dipole is indicated by the quantity, physical quantity, electric dipole moment. Okay, all of you know that. So what is the formula for electric dipole moment? You know that electric dipole moment P is equal to Q times the distance between the two charges. Magnitude of charge into the distance between the two charges, right? This is the equation for electric dipole moment. All of you know it. Electric dipole moment, right? Remember, length 2L is, you can measure from negative charge to positive charge. That means it's a vector. So dipole moment is also a vector. It is directed from negative charge to positive charge. These are all, I have discussed this in the previous classes. So all of you familiar with these ideas. What is a dipole? What happens to a charge in an electric field? Okay, now in this session, what we are going to understand is, instead of placing one charge, we are going to place a dipole in an electric field. Dipole in an electric field. So there are two cases. You know that electric field can be a uniform electric field or non-uniform electric field. The result will be different. If you are keeping a dipole in a uniform electric field and non-uniform electric field, the result will be different. In this session, we are going to understand what happens to an electric dipole in a uniform electric field. In a uniform electric field, what happens to an electric dipole? Okay, so let's begin with a uniform electric field. You know, what is the meaning of a uniform electric field? To say an electric field uniform, you know that its magnitude and direction should be the same everywhere. So if you're considering a region where uniform electric field is present, means the magnitude and direction of electric field intensity should be the same. And you know that a uniform electric field is represented by equidistant parallel lines. That's a way of representing uniform electric field. You know that. So let us take such an electric field. Okay, a uniform electric field. Magnitude and direction is the same everywhere. So listen. So we're going to begin with a uniform electric field. Look at this. So I'm going to use some equidistant parallel lines in order to represent a uniform electric field. Yeah, dear students, look at this. See, this is the representation of a uniform electric field, and from the diagram, what are the idea you are getting, or what are the things which you can point out about this electric field? Clearly, since it is represented by equidistant parallel lines, we can say it is a uniform electric field. Again, what is the meaning of uniform electric field? Magnitude and direction is same everywhere. So if I'm marking a point in this electric field, for example here, I'm marking a point, it as A. At the point A, if the intensity of electric field is E, then at another point B, at some other point C, everywhere the magnitude of electric field will be E itself. That's the idea of what? A uniform electric field. So that is one thing you can understand from this diagram. It represents a uniform electric field. And another thing is, what is the direction of this electric field? You can see that these are electric field lines, and it is directed from left to right. So field lines are directed from left to right, which means the direction of electric field is also from left to right. So those two ideas everybody can easily understand from this. This electric field is uniform, it is directed from left to right, left to right. So whenever you are looking at the diagram of an electric field, please understand, please note that you know the direction of electric field. Normally it starts from positive charge to negative charge, right? In this diagram, I did not show the source. I did not show from where this electric field is generating. I did not show any source charge in the diagram, but that idea should be there in your mind. The electric field lines are starting from positive charge and ends at negative charge. That means in this diagram, please keep in mind left side, which charge will be there. Since field lines are starting from positive charge, left side there will be positive charge and right side there will be negative charge. So please keep that idea in your mind. Remember, left side there will be positive charge and right side there will be negative charge. Okay. Idea is clear. So this is representing a uniform electric field. Now what we are going to do is we are going to place a dipole in this uniform electric field. A dipole. Once again, what's a dipole? It's a pair of equal and opposite charges separated by a small distance. So look at this. So I'm going to bring a dipole and I'm going to place it in this electric field. Look at the way in which I'm going to place this electric field. Dipole in this electric field. Look at this. This is how I'm going to place. So there is a chance of a confusion. What is this line representing? This line is representing a dipole. Look at this. This is one end of that line. This is the other end. So I'm going to make it as a dipole. For that, what I'm doing is, look at this. Here, I'll be placing minus Q charge, minus Q. And here, plus Q. So clearly it's a dipole, right? So you may think that why can't we keep it straight? See, the orientation is our choice. You can keep in whichever orientation you want. You can keep it vertically, you can keep it horizontally, you can keep it at any angle. So I'm just taking a position like this. So you can see that it is not parallel to the electric field. It is not perpendicular to the electric field. It is at some angle with the electric field, right? Some angle. I told you that's our choice. So here I'm going to take that angle as, in this diagram you can see that this is the angle. That angle I'm going to take as theta. Okay, so I'm again telling you that theta can have any value. It can be 0, it can be 90. Okay, it can have any value, 30, 60, any value is possible. So we are just taking a general notation, theta. So this dipole is making an angle theta. Now here you can note another important point here. Look at this. Direction of electric field is from left to right. Direction of electric field is from left to right. Remember, electric field is a vector. Direction of dipole moment is from negative charge to positive charge. So clearly you can see that electric field is directed in this way and dipole moment is directed in this way. So what does theta means? We can define theta in another way. It is the angle between vector E and vector P. What is vector E? Vector E is electric field direction. Vector P is dipole moment direction. So clearly theta is the angle between electric field vector and dipole moment vector. So vector E and vector P. So that also you have to keep it in your mind. It is the angle between vector E and vector P. Theta is the angle between vector E and vector P. Okay, so I think the situation is very clear. Now see, what's our aim? We are going to understand what happens to this dipole in this electric field. Okay, see, this electric field consists of two charges, minus Q and plus Q. All of us know that when a charge is kept in an electric field, it will experience a force. So here, how many charges are there in a dipole? There are two charges. Minus q is there, plus q is there. So surely both of the charges will be experiencing some force. Okay, so let's take one by one. All of you concentrate on minus q charge. Minus q. Minus q. Minus is its sign. What is the magnitude of the charge? Q. Magnitude of the charge is q, isn't it? Yes, q is the charge. So q charge is kept in an electric field. What is the magnitude of electric field? Magnitude of electric field is E. We have taken it is E is the magnitude of this electric field. So a charge q is kept in an electric field of magnitude E. We know that it will experience a force. What is the magnitude of that force? We already found it. It is QE. So what happens to the charge is minus q charge means we can write it will be experiencing a force F is equal to Q times E, QE. It experiences a force F is equal to QE. Clear, right? QE. Magnitude of the force will be QE. Now, apart from the magnitude, you should have an idea about its direction also. See, Q is experiencing a force which is QE. Now, what will be the direction of? For that only, I told you, keep in your mind that this electric field is directed from positive to negative. So you can see left side there is positive charge and this is a negative charge. So negative charge will be attracted towards the positive charge, right? Minus and plus. Force will be attraction. So what is the direction of the force experienced by this minus q charge means surely it will be attracted towards left. So you can show the direction of that force in which way? It is acting towards left. So look at this. The force is acting towards left. What is the magnitude of the force? It is QE. So minus q charge is experiencing a force QE, but it is acting towards left. Okay, now come to plus q. Plus q. Again, the magnitude is q. Only the sign is changing. So magnitude is q means what will be the magnitude of force again? It's a uniform electric field. Electric field is same. Charge is same. So the magnitude of force will be again QE. There is no change in the magnitude. QE. Minus q is experiencing a force QE. Plus q is also experiencing a force QE. So both the charges are experiencing what? Equal amount of force in magnitude. Okay, but what about the direction? See, come to this plus q charge. This is a positive charge and you know that this side there is negative charge. So this positive charge will be attracted by the negative charge. That means the charge will be attracted towards right. Okay, so you can mark the direction of that force in this way. Interesting, right? This minus q charge is experiencing a force QE, which is towards left. Plus q charge is experiencing a force QE, that is towards right. So what can we see? Is there any other forces acting on this dipole? No, because only there are two charges. Both the charges are experiencing forces. But when you're analyzing these forces, you can see that both the charges are experiencing equal amount of force, but they are acting in opposite direction, exactly opposite direction. One is acting towards left and the other is acting towards right. So since they are equal and opposite forces, tell me what will be the net force acting on this dipole? It's like we'll call it as opposite, unlike parallel forces, right? What will be the net force? Clearly the net force will be zero. Dear students, it's a very important point. When an electric dipole is kept in a uniform electric field, what is the net force acting on that dipole means? The answer is zero. F net is equal to zero. And what is the reason for that? The reason is there are equal and opposite forces. Net force acting on it will be zero. Clear or not? Yes. Now the question is, okay, net force is zero. Does it mean that this dipole will remain stationary? That means in this initial position like this, the answer is no. Why? Because if you are analyzing this diagram, you can see that the top part, that means this part of the dipole is experiencing a force towards right and this part is experiencing a force towards left. So you can assume it's just like a stick. On the top of the stick, there is a force which is acting towards right and bottom of the stick, the force is acting towards left. Okay, so what happened to it? This will be moving this side. This end will be moving towards right and this end will be moving towards right. Remember, net force is zero, but there will be forces acting on the top here and bottom here. So what happened to it? Normally, you know that this kind of situation comes means the stick, if you're considering it as a stick, the stick starts rotating, right? Rotating. Very, very important point. Even though the net force acting on this dipole is zero, we have to say that this dipole will rotate in this uniform electric field. Rotation. You know that in 11th you studied in detail. To rotate a body, we should apply what? To rotate any object, a torque should be there, right? Or a torque only can rotate a body. So clearly, this dipole is rotating means we can say that this dipole will be experiencing a torque. This is the answer to the question which we begin with. What was the question? What happens to a dipole in an electric field, in a uniform electric field? We can say that when a dipole is kept in a uniform electric field, it will experience a torque. Now we are going to calculate the magnitude of that torque. I hope you understand why it is rotating, why torque is experienced. Okay, so the top side will be experiencing a force in this way, bottom side is experiencing a force in this way. As a result, it starts rotating. This side will be going like this will be going in this way. So it will experience a torque. Now we are going to calculate the magnitude of this torque. For that, we have to go to the 11th grade idea of torque. What is the formula for calculating torque? Couple. You know that in this kind of situation, torque can be calculated. The basic formula for torque is magnitude of force. So what is the force acting on this, right? Magnitude of one of the force into the perpendicular distance between the line of action of two forces. Magnitude of force. So I'll be writing that equation here. Torque tau is equal to magnitude of force into what? The perpendicular distance. Magnitude of force into the perpendicular distance. Okay, perpendicular distance between what? Perpendicular distance between the line of action of two forces. So all of you look at this diagram again. Line of action. See, if you are looking at this diagram, you can see that the first force, force on plus Q, is acting towards right in this way. That means the line through which that force is acting, surely this is the line in which that force is acting, right? So line of action of forces represented by that dotted line, you can see it. So this is the line of action of one force. It's acting parallelly. And what is the line of action of the other force? That means force on the negative charge. It is also, you can represent using a dotted line. Look at this. So this is the line of action of the other force. Very clear. One force is acting in this way. This is the line of action of one force. The other force is acting in this way, right? Towards left. Okay, so how to find the torque? Torque is equal to force into perpendicular distance between the line of action of two forces. Now, what is the magnitude of force? We got it already. It is QE. So, I'm going to write F is equal to what? QE into perpendicular distance. So, here don't be confused. We don't need the distance. We need the perpendicular distance. See, looking at the diagram, you can see this is representing the length of the dipole. Length of the dipole is normally denoted by 2L, right? So 2L is the length of the dipole. Okay, but is it the perpendicular distance between the two, line of action of two forces? No, one is acting in this way, other is acting in this way. So this is not the perpendicular distance. It is some other distance, right? It is the distance at an angle. Perpendicular distance means we have to take which distance? Perpendicular distance means this one. So we need this distance actually for finding what? Torque. See, this is the line of action of one force. This is the line of action of the other force. Perpendicular distance means this one. Okay. So we have to find that distance. For that, what I'm doing here is I'm just giving some name for this. I'm taking this point as A. This point I'm taking as B. This point I'm taking as C. So you can see there is a triangle ABC is there. In that triangle, which side is the perpendicular distance? Surely it is a side BC. Okay, so you can write QE into what? BC. QE into BC. Now we have to find the value of BC. Okay, look at the diagram again. Look at this triangle ABC. We have taken this angle as theta. If that angle is theta, surely this angle will also be what? Theta. So in triangle ABC, you can see there is theta. Take sine theta from it, okay? Sine theta. What will be sine theta from this triangle ABC? Look at this. Sine theta is equal to opposite side by hypotenuse. What is opposite side? Opposite side is our BC. BC divided by the hypotenuse. Hypotenuse is AB, right? AB is the hypotenuse of this triangle. But what is AB? AB is nothing but the length of the dipole. It is 2L. So look at this. It is BC by 2L. So you can see that BC is equal to what? 2L sine theta. BC is equal to 2L sine theta. 2L sine theta. Now you can substitute that value of 2L sine theta over there. So It is equal to Q into E into what? 12 sine theta. 12 sine theta. Okay. QE into 12 sine theta. Now you can see another interesting result here. Q. What is Q? Magnitude of charge. Into 12. What is 12? Distance between the two charges. Magnitude of charge into distance between the two charges. What is it? We know that Q into 12 is the dipole moment P, right? So in this we have an equation QE into 12 sine theta. What is Q into 12? Dipole moment P. So you can replace that Q into 12 by the letter P. So we can see it is P into E sine theta, right? PE sine theta. Okay, this is the torque. Magnitude of torque, we got it is PE sine theta. So clearly you can see that what are the factors affecting the torque acting on a dipole? Dipole moment, strength of electric field, orientation, angle. So when angle changes, torque value will also be changing. Now if you are looking at the final equation, PE sine theta, what is P? Vector, right? Dipole moment vector. E, electric field vector. Theta, angle between P and E. So just like you can see that first vector into magnitude of first vector into magnitude of second vector into sine of the angle between first and second vector. Do you remember this kind of formulas? A, B sine theta. If A is the first vector, B is the second vector and sine theta, it is representing the cross product of two vectors, right? So using that idea, we can write a torque in vector form. How means vector tau is equal to vector P cross vector E. Vector tau is equal to vector P cross vector E. I hope it is clear. So again we can go back to a question. Question was, we started with a question, what happens to a dipole in an electric field? Answer is, it will experience a torque. What is the net force experienced by a dipole in a uniform electric field? The answer is 0. What is the magnitude of torque? Torque is equal to P cross E. It is equal to PE sine theta. Okay. Now there are some special cases of this, what happens, I mean at different angles, what will be the value of torque and all, that we will be discussing in our next session. Hope all of you understand this session. Thank you very much. Take care.
Brilliant Qatar, your trusted coaching partner for IIT, JEE, NEET, Science and Commerce tuitions with 10 years of excellence in quality training. Brilliant Qatar.